Welcome back everyone. In this lecture actually I will prove some of the basic properties of groups. So we were actually seeing some concrete examples of groups and subgroups, okay. But it is also important to learn how to approach this group theory abstractly. So that is why I would like to prove some of the basic properties of groups in this lecture. Okay, so let us start with a group G. So that means group actually comes with this binary operation star. So this we take it as a group. So recall that. So this star is actually a binary operation. So that means it is a map from G cross G to G. So it is a function. So what we did, given AB, we actually associated some element inside G, we called it A star B, okay. So since we are actually, I want you to get familiar with abstraction. So whenever I say group, we will actually start ignoring this notation star in what follows next, okay. So for example, so we just assume star is there. And then start writing AB instead of A star B, okay. And I also want to introduce some notation. So we denote E by the identity element, okay. So I already told you the identity element is unique. So in this lecture I will prove it is unique, but anyway it is not that hard exercise. So this is identity element of G, and given A in G, the inverse of A. So I also told you that inverse of any element is also unique. So the inverse of A is denoted by A inverse, okay. So these are all the standard notation that we use. So this one and this one, okay. So let's start with the identity element, okay. Let us try to prove its uniqueness, okay. The identity element is unique, so that is the fact one. Identity element of G is unique, okay. So what is the meaning of that? So that means if you have two elements of the group G that satisfy the property of the identity element, then those two elements must be unique. So let us call E and E dash. So they are the identity elements, okay. So that means they satisfy the property of identity elements. So what is it? For example, AE and EA should be A for all A in G. So this is the property of the identity element, and the same thing should be true for E dash as well. So AE dash E dash A should be equal to A for all A in G. So now note that I can take simply so this you call it equation 1 and then this you call it equation 2. So if we take A equal to E dash in the first equation, in the equation 1, so then we get E dash E equal to E dash equal to E dash, okay. And if we take A equal to E in the second equation, so then we get the following: E dash equal to E dash E equal to E, okay. So now if you put them together, so for example E dash is appearing both places. So E dash, one hand you are getting E dash On the other hand, you are getting E. So, because these two are must be same, so that comes from the definition of the function. So, given E dash, then that element that is associated with E dash, okay. So, that must be unique. So, that tells you that, so this E dash must be equal to E. So, this proves if you have identity elements, okay, two identity they must be same. So, that means the identity element of G is unique. Okay. So, similarly one can prove actually the inverse element of inverse of any element must be unique. So, this is I will again prove. So, this is the abstraction that you start appreciating. Okay. So, you start with an element A in G. So, what we want to say? We want to say that there exists unique inverse for this element A. So, let us say there are two elements B1, B2 in G such that both are inverse. So, that means A B1 and B1A must be equal to identity, and similarly A B2 and then B2A must be equal to identity. So, this is what you have. Okay. So, now what we want to prove? So, we want to prove that B1 and B2 both are equal. So, this is exactly like cancellation. Okay. So, basically you want to say that if you have equation something like this in a group, you will be able to do cancellation. Okay. So, now let us see how one can prove this. So, we have to use property of the identity element as well. So, you know that B1 is same as B1 identity, okay, but identity is same as B1A or B2A. Okay. So, basically you start with B1 and then you say that B1 is same as B2 by introducing these new elements in between. So, you have B1E. So, let us try doing that. So, you have this identity. For example, what I can do? I can substitute instead of identity, I can substitute for example this A B2. Okay. So, then B1 identity will becomes B1 A B2. Okay. So, now you can see that this B1A which is again identity. So, then I can replace this B1A by identity and then I will get B2. But E times any element is itself. So, then you get B2. So, just rewriting B1 equal to B1 identity and then substituting identity as B1A, you see that you can actually go with this argument and then show that B1 equal to B2. So, that means given A, there exists unique B in G such that AB equal to BA equal to identity. So, that unique element we denote it by A inverse. Okay. So, that is how we introduce this notation. So, because both identity and the inverse they are unique. So, we are comfortable in this introducing this. Okay. So, like I was telling about this cancellation that can be done in the group. Okay. So, let us just formulate it more mathematically and then prove it. So, this is the fact 3, which is again very useful fact that you can actually use left and right about groups. So, because we can actually talk about inverse element for each element. Okay. So, I will be able to actually cancel any element if it is in the some equation like this. So, what I mean by that? Let us say you have AB1 equal to AB2 for some A B1 B2 inside G. So, you have some equation like this. Okay. Sometimes you will have equation like Ax equal to B minus, that kind of linear equation you must have seen. So, similar to that we have this equation. Now, we do not know like what this group or what this ABs and all. Okay. but we are saying that there is such equation abstractly. Okay. So then what I want to say, if this is happens, so then so because A has inverse, I will be able to multiply by the inverse of A on the left side. So that would actually imply that B1 must be equal to B2. So I am allowed to cancel A and then get B1 equal to B2. So don't do anything crazy like this. So you are not allowed to subtract something like this. Okay. So this is not allowed. So let me just write it completely. So this is what you do when you see linear equation, but this is not happening here in the group. Okay, because we have only one operation that is called the star. So by abuse of notation, we are just writing, instead of A star B1, we are writing A B1. Okay, so there is no meaning of subtracting AB1 minus AB2 and so on. Okay, and then you can't take A out, like B1 minus B2 equal to 0 and then cancel A. So that is, those things are not allowed. But how do you make sense? But still we are saying that B1 must be equal to B2. So how one can prove this? Okay, in the group setting, let us see here. So here is the proof. So you start with this equation AB1 equal to AB2. So that means what we are saying, if you take A comma B1, the image of that is same as A comma B2 under this star map. Okay. So now what I can do, this is one element, this is one element that inside the group G. So I will be able to actually take A inverse and then apply, okay, or I can do the multiplication with A inverse. So I say multiplication, but what I mean is binary operation that we perform on the group. Okay. So we just abstractly talking about something multiplication. So not the usual multiplication. Okay. So you just take A inverse and then apply it on the left side. So then what do you know? So this has to be equal to A inverse that you apply it on AB2. So this you can do just because the star is a function. Basically, so this element is the image of A inverse comma AB1. So that this is the image of that. Okay. On the other side, you have A inverse comma AB2. So since AB1 is same as AB2 and these two tuples are same. Okay. This is same as A inverse AB2. So the images of these two must be same. So what is the image? So that is like star of A inverse comma AB1. That should be same as star of A inverse comma AB2. So the images should be same. So that is what we just call it A inverse AB1 and then here A inverse AB2. Okay. So now you have this element, but you have what is called associativity. So this is same as A inverse A and then B1. Similarly, this is same as A inverse A B2. But when you take A inverse times A, you know that that is already identity. So this becomes identity times B1. Similarly, this becomes identity times B2. Okay. But identity times any element is itself. So here you get B2 and here you get B1. So this proves that B1 must be equal to B2. So I am allowed to do cancellation. Okay. But when I say cancellation, not cancellation like this. Okay. So this is not what I mean. So here I can multiply by A inverse on left side. So I am able to do the cancellation. So similarly, one can do what is called right cancellation. So if we have equation like this, B1A equal to B2A and for some A B1 B2 in G. So then what we get? So then we get that B1 must be equal to B2. So again, how the argument goes, it's very similar to what we did before. So the proof is just one line. You take B1A and then multiply with A inverse. So then you get B1 on the left hand side. On the right hand side you get B2A and then you multiply with A inverse. So then you get B2, because this A inverse becomes identity. So you get B1 equal to B2. So when you are doing it for first time, I would recommend not to miss any steps. Better you just go through step by step and then see what properties of groups that you are using to justify each and every step. Okay. So this is something about the cancellation. So now let us try to understand this associativity. So I already explained the consequence of associativity in the very first lecture when I introduced this set of all moves on the given Rubik's cube. Okay, so that is something I want to again emphasize here in very abstract sense what it means. So recall, so what is the associativity? So associativity says, if you given 3 elements A, B, C inside G, so we can actually perform 2 different possible products. Okay, one is I can first multiply AB and then multiply C. Okay, and then I can multiply first BC and then multiply A. So what I mean by this, I simply consider the images. Okay, so you take star of first A comma B and then take star of A comma B comma C. Okay, this is the element that is there on the left side. But if you think about it, what is on the right side? It is star of A comma star of B comma C. So I am denoting, okay, the star is a function from G cross G to G. Na? So given AB, I am denoting star of A comma B by the image. We also used that A star B, but I want to just use star of A comma B. This is the traditional notation. For example, if I call it this F, okay, star as F, then what is A comma B image? It's F of A comma B. Okay, that is why I want to write it like this. So, but once you are very comfortable with we are talking about abstract binary operation, then you can just simply suppress the notation and write it as AB. Okay. So that is why you, so but you can see that, so this is first you are taking some image of AB and then considering image of this image of AB comma C. So that could be very different from what is on the right side. Okay. So in that case there is no guarantee that these two products need to be same, but in group theory, in groups we are actually demanding that these two are same, because many examples that we know, for example matrix multiplication, addition, all of them satisfy this associativity law. So that is why we demand this to be true. Okay. Okay. So now let us start with 3 elements A, B, C, D inside G. So then you can see that now there are more possibilities of taking these successive brackets, okay, or the products between these elements. So the order that we don't change, the A, B, C, D remains same, but the way you actually kind of perform, like there are like the brackets you can adjust, and then there are many ways actually you can actually take the product. So what I mean by that, for example, I can first multiply AB and then multiply CD, okay, and then take this product. Okay, you take this one and then this one and then take product between them. So that is allowed thing, na? Okay, and then you can also do something like this. I can keep A as it is and then I can multiply CD first and then BCD next, and then I can multiply with A with this. Okay. So, but what do we want to say? It doesn't matter how you actually group them. Okay. Once you fix the order, this A, B, C, D, so then these elements will be same in the group. Okay. So, I will leave it as exercise to think about how many possible brackets that you can actually, or how many ways you can actually get elements from the given this ABCD. Okay. So, you fix this ABCD in G. So, now, so not exactly in G, what I am talking about, the number of possible groups that you can make. Okay. So, find out how many possible grouping, okay, we can do. For example, so this A, B, C, D, so this is one grouping, and then A, B, C, D is another grouping, and similarly A, B, C, and then D another grouping. Okay, like that you can perform many grouping. I want you to find out how many are possible. And given of course, once you are done with 4 elements, you can also try to do it for 5 elements and so on. And it is not that hard to actually find out a formula for any given finite number of list of elements. So, what I mean by list of elements, you fix some order. So, like A1, A2, etc., AN, and then we can actually talk about possible like grouping like this. Okay. So, I will actually include that in the problem sheet. You may think about it. But what is interesting, okay, fact. So, once you assume this associativity, okay, so then you can actually convince yourself that these two elements, for example, they will be same inside the group. Okay, it doesn't matter the order in which you group the elements. So, as long as you fix the original order like A, B, C, D, okay, the way you group doesn't matter. So, you still at the end you will be getting the same element. So, that is because of associativity. So, this can be proved using induction, okay, and then induction on the number of elements that actually appear. Okay. So, maybe later I will actually discuss about this, but for 4 it is very clear like what I am talking about. So, let us do this small examples and then see, and then we will get to some idea what to do with the general case. Okay. So, let us consider this A, B and then C, D. So, one possible bracket I said you can do something like this. Okay. So, but the thing is this B, C, D, like it does not matter the way in which you bracket them. Okay, they are same. Na? For example, this tells immediately that. So, if I group them in some other order like A, B, C and then D. So, since this B, C, D, this element that I have written here is same as this element. So, again you are bracketing with A. So, it tells you that these two are actually same. Okay. So, now what happens? So, now you see that this is same as. So, what we wanted to do like yeah, so maybe like we will verify that these two are same. So, grouping A, B, C, D and then this A, B, C, D. So, those two are same. So, how do I do that? So, again you start with for example, the left side. So, A, B, C, D. Okay. So, this you can now think as one element C, D. So, that is like X. Okay. So for example, I call this as x, so then this becomes ABX. So this is what this x. So now using associativity, you can see that this is same as ABX. Okay, that is what associativity tells. So that means this is same as ABCD. Okay, because CD is your x. So this CD is your x. So that tells you that this element is same as this element. So this is something we verified. So this is how you verify actually for all other elements. But writing down the proof is actually a bit technical. It uses induction. It's not that hard. One should learn how to write down the proof as well. Okay. So maybe I will do in one of the problem solving section. So you can actually convince yourself that all these elements are same. Okay. So convince yourself all the elements that you get are same for just length 4. Okay, for length 4. So that means only given ABCD. So you are considering all possible brackets like this, na? But it doesn't matter which bracket you take, still you will be getting same element. That is what I am saying. So that unique element, okay, so that is denoted by just ABCD. Okay, because the way that we group them doesn't matter. So you just write them as ABCD. Okay. So in general, what we do, in general, given A1 etc. some AN inside G, so you write A1 product etc. AN. Okay. So or we can also use this notation, but this arrow matters a lot. So because the product is taken in very specific order. So that is what this arrow means. So this is actually a symbol for product. Okay, this is just symbol for product. And when we put arrow like this, then this means the order in which the product is taken matters. Okay. So then you can say this is just AI. So basically product, you can put AI and then just arrange it from 1 to n. So either you denote it by this or denote it by this, not a problem. Okay. So this is what associativity actually guarantees us. Okay. So yeah. So these are the some basic properties that I wanted to discuss today. So I will stop here and then I will continue with more properties in the next lecture. Thank you.